2, 3, 4, 7, and this is 2, 2, 3, 4, 8. That's not a match. So I set 3, now I have 2, 2, 3, 4, 7. S1 and S3 match now. Okay? Now I'm going to do this separately here, and then I'm going to have 3 different rows of these bands. And so if S1 and S2 fail here, that's not necessarily so bad. I can check again if it matches in all 3 of these bands, and in any of these other bands as well. So I check if it matches in any of the bands. Okay, so basically how this works is you have bands of B hash functions, and you have and you're going to have R rows of bands. So you can say something like it's similar if for any band you have all collisions in the band, right? So this was so this was the Mama Bear technique, and this was the Papa Bear, right? So you have, for inside the band, you need to have all the collisions, but you have many choices. You can be a bit more forgiving. You don't need to hit any one of the, in all the bands, you just need to hit one of the bands. So Papa's a little harsh, and Mama's more forgiving. Okay, so hopefully this should seem like it should intuitively work. You can do this quickly by, as I said, you can do kind of both of these efficiently by themselves, but neither of them is really getting, this one was too harsh, this one was too forgiving, right? So how this works is you have R of these different bands, and for each of those bands, you're essentially setting up a hash table. Okay, and in the hash table, the entry is defined by all B, in this case, all 5 of the entries of the 5 different hash functions. So this is kind of like a 5-dimensional grid. So I've divided up I've got this k-dimensional space. It's a 15-dimensional space. Kind of hard to think of a 15-dimensional space, but we'll work on this. And so you've kind of gridded this up, and you need to hit exactly in the cell. In the same cell as another one for it to count, because each cell will map to a different cell in a hash table. You can have you can have infinite number of these cells essentially. The hash table only needs to be as big as the number of entries in it. So, and if this one doesn't work, well then you can try again with a different one of these bands. So your 15-dimensional space is now in R of these different grids. And those grids are independent from each other. Okay. So this kind of is some way of seeing the intuition. Another way you'll see it is you'll actually do this in the homework, and you'll kind of see how it works. Let me try and go through a different way, and I'll accompany this by some stuff on there. Yeah.
So by band you mean from 1 through 5 in case of the Papa thing. So all of them have to match.
Yeah.
But any band means just one of those, like H3 can match, and then it's considered equal.
That's right. So if band 3 matches, then I say that these are similar.
The whole thing is a band.
So this is one band, this is one band, this is one band. If any of them match, I say that they're similar.
So the comparison you made between H1 and S3 is for the first version.
H1 and H2.
No, S1 and S3.
Oh, S1, S3, yeah. So this is just in this one band.
So it's matching this one band.
Yeah. But I've got other opportunities, and these are independent, right? These hash functions should be drawn independently at random from the hash family. So these are independent trials, right? So this, if I just look at one hash function, I have some probability, right? So if the similarity is defined here, the probability I have a collision is going to be exactly what the similarity is, right? So the thing is, if the similarity is 0.5, that means half the time I'm going to find it. What I really am going to want is a curve instead that's going to look like this, okay? And I want it to be really sharp. So if the similarity is above a threshold, I want to find it with really high probability. If it's below the threshold, I want to find it with, say it's there with a low probability. And then if I find it, assuming the number of similar items is small, based on you say your threshold, you can even go and check the ones that came up as similar and calculate that exactly. But sometimes just using this will be enough. But I want to change this probability from being this linear thing to something that kind of is more of an S shape. Okay, so let me try and look at this a different way by walking through how the probabilistic argument works here. Okay, so I'm going to start using the Jacquard similarity, and so we're going to have S is going to be equal to the probability of collision. Okay, so this was based on the similarity is the probability of collision, so I'll be sticking to this case. So that means that S to the B, right? So S to the B is now going to be the probability that all hash functions in one band will collide. Okay. And so 1 minus S to the B is going to be the probability that not all hash functions in one band collide. And then 1 minus S to the B to the R. Okay, so this is going to be the probability that no collision in any band. Right, so I have R of these bands, and each of them are independent. Right, so this is the probability of no collision in any one band. This is the probability of no collision in any of the bands, in all R of the bands. And then finally, the probability that I say that they're similar is 1 minus, and I'll write this bigger on top in a second. So this is, so the final thing I want here is going to be 1 minus S to the B to the R. Right? So this is going to be the probability I say that they're similar. So this is the probability that I declare that they're similar. Because 1 minus this was the probability of no collision in any band. So if I 1 minus that probability is the collision in at least one of the bands. Okay, and that means everything in that one band collided. So now these two parameters B and R are controlling this. And so this red value here is going to look like this black curve here. It's going to be an S shape. Okay, so let's see an example of this. Let me walk through this a bit. So, okay, so let me So I start with my similarity, and I'll use x, it's this black line here. Right, now if I go x to a, or in this case, a is going to turn out to be b. Let me do b here. So if it's b is equal to 1, I still get this curve. If b is equal to 2, you know, the probability, now if I have, if I have two, if I require to hit in both of them, the probability drops. Yeah.
In your notes, your R and your B are switched.
Yeah, I realized that just a minute ago.
Okay.
I'll stick with R and B this way for the course of the lecture, but yeah, so in the notes I have them switch where B is the number of bands instead of the number of elements in the band. I think that's the more standard way is the way in the notes. So I'll probably keep those as is. But sorry, I realize I do have those switched. Okay, so as I'm increasing this value b, the probability of all hash functions is just keeping increasing, right? Or is decreasing, the probability of collision all of them, right? So if I bump this up to 5, I went from, if my similarity was 1/2, I had a 50% probability of having collision. Now I have something like a 5% probability. Right, so that's what's going on. Okay, so now I want to do you know, 1 minus this, and now I get the opposite, right? So the probability of not colliding. And then if I take this to the value r, R seems to be, I'm going to use A instead. This program does not like R's. Okay, so saying to 1 doesn't do anything. If I set it to 3, so what's happening is this is coming down. I'm having, this is again the probability of not having being similar. Let's get it to the right way. So now I have this S curve, right? So now this is the probability of, this is the probability of declaring it similar. So let's see what happened again. If I have A equals to 1, then because I had a larger, I used all my hash functions, all 5 of them inside the band, the probability dropped to being similar. Right? But now I have 3 different bands, the probability went up. And as I keep increasing this, the probability keeps going up. And actually what this R parameter is doing is it's sliding this over to the left, this kind of thing. So it's raising the probability, but when the similarity is high, it's already pretty close to 1. So what it's really raising only the probability in this part, and it's really sliding this kind over. Okay, so let's see what happens when I mess with this B parameter. I'm going to, if this goes down, then I'm also sliding it further to the left. So if this goes from 3 to 5, then the probability is going down. It goes up to 15, the probability keeps shrinking. But as these numbers get higher, what's happening, this S curve, is it's being much higher slope. It's being much sharper. The more hash functions I use, I'm kind of getting a much, a much sharper divide between being declared similar or not similar based on whatever the similarity is. Remember, the x-axis here is the similarity of the two things I'm comparing, and the y-axis is the probability that I've successfully declared them being the same. Right? So the more I use, it's somehow becoming sharper. I'm getting a better divide. But you'll notice, I have 2 parameters, and if I have 15, and really I have A times B, right? So let's say I divided A by 5, and I added this onto B here. So this became 75. The effect is I shifted it all the way to the right. Let's move this back to 15. This is 25. and let's change this one to this to 5 and this to 75, and it's shifting it to the left. Right? What I get to do is I get to kind of control where this threshold is of what I decide is similar. I have some similarity threshold, you know, sitting, say, maybe I want for this similarity threshold right here. These are how I want to distribute it into bands and rows. I kind of need to play with this to figure out the right way to distribute these. But I need to use both of them in order to kind of get this sharper threshold. Okay, so how do you choose the values of R and B? So you kind of want to, the threshold that's maximized is, and I'm not going to go and drive this, is roughly where the slope is the steepest. It's roughly going to be 1 over R to the power 1 over B. And so then, if I want to, so given B and R, that kind of tells me where the threshold is, right? So in this case, let's see, 1 over 75 to the power 1 over 5, and hopefully, if someone wants to type that in a calculator, hopefully it'll give a threshold value somewhere in here. Hopefully it works in my example. So this is kind of a rough approximation. So in order to set, so for a given similarity threshold you want, so remember you only have one parameter. If you choose the value R, then, or the value B, then you're given a fixed number of these hash functions, right? So typically, a good choice would be to take B, and then for the so set B equals to the base of this similarity you're hoping to kind of find as your threshold of K, and then R is going to be defined as K divided by B. Right, so you kind of, this is kind of a good rule of thumb on how to set the values of B. So take log of base S of the number of hash functions you have and use that as B. And that's a fairly good one. So you're going to have a lot fewer bands typically than you are going to have, or a lot fewer things in a band than you are going to have different rows. Yeah. Okay, so this is, so again, this, I don't know, this maybe this kind of seems like it's pretty crazy. There's lots of math going on here, but you know, it's really, you know, it's not that hard to actually use, right? You have all these hash functions, and you break them into groups, and if they all match, then in any one of the groups, then you declare it similar, and you have to choose how many groups to break them into in order to kind of capture the right similarity.
So this is of the order of the number of dimensions we have.
The what?
And number of dimensions we have.
So K is like the number of hash functions you have, so the number of dimensions of your vector.
Okay, so if suppose we have less number of grids, say the total grids which are there are less than the dimensions. So can we reduce this problem from dimensions to the number of grids, because the grids are smaller?
So what do you mean by the number of grids?
The grids that you
Well,
make.
the number of grid cells, or the number of...
Yes, for each hash function.
Yeah, so the thing is, I haven't really, so the number of grid cells is actually here is like, I haven't specified it, right? I could have a large number of possible items here, right? So if I have smaller, so in the case of this Hamming distance, which we're using for the Jacquard similarity and sets and so forth, I need this match to be exact. This match to be exact, right? So if so you're saying
if dimensions are more and grids are less?
So the grids, yeah, so say I only had two possible values, either 0 or 1.
Yes.
So actually there are some, there are some other distances where you actually do this. So we'll talk about the cosine distance a little bit, which is also used a lot for text, and I'll talk about this on next Monday. And for the cosine distance, you actually do use essentially a grid that has, for each hash function, it's either -1 or +1. And this works within this framework. And you can actually do that for a lot of settings, reduce it to a small number of grid cells. You still need a lot of dimensions. I'm not sure if you can somehow get some advantage out of that. So that's an interesting question, but I'm not quite sure how it would work. I'm skeptical, but maybe there's interesting question. So okay. So does this general scheme seem pretty simple? You have all these hash functions you've created for your min hashing, and you're just grouping them and checking if in any group things match exactly.
And is the main advantage of this speed?
Yeah. So let's look back at these questions. Yeah. So the main advantage is definitely speed, right? So which documents are similar, right? So how would you use this to do which documents are similar? Right. So for each of the rows, you have R of these rows, right? For each of the rows, you're going to create a hash function for you're going to create a hash table. So for each of the possible combinations of the B values, it's going to be a cell in the hash table. And if for any row two things wind up in the same cell of the hash table, then you declare them similar. So you make one pass over all the data. So instead of checking all pairs, you make one pass over all the data and throw them in these hash tables. And then you go back and you read off the hash tables, and for every bin, every non-empty bin, if there's more than one thing in there, you say all those things are similar. So you've kind of gone from n squared to n, linear. You've gone from a billion comparisons to a linear number of, for each of the items, you have to do these k hash function calls and put it inside these hash tables. But assuming that's some small enough constant, it's much less than doing an extra million amount of work for each of those things. So this part becomes faster. So in the question 2, how would you answer this? Well, so you wanted to find some threshold similarity, and then you choose how to divide up your bins, your hash functions in these bins and these rows. And then you've already done this with all your existing documents. You've done some pre-processing with them. And so you've put them in these R hash tables. And then you just, for your query, you check each of those R hash tables, and for any bin it falls in, if there's anything else in there, you say that one is similar. So that, again, it only takes essentially R time, the number of, for each of the hash functions, you just need to call those hash functions on the new query point again, and you automatically get the similar items. It's similar to kind of looking up in this grid cell. I can go and index with the pointer to this grid cell, and then say which are the other elements stored associated with that grid cell, like a list or something. So I can just read off the similar items. So the speed is the big advantage. So, this is a good question. So I started with documents where I had all of the information about all the stuff. I've done some modeling and got it with these k-grams, got down to these sets. And then these sets kind of, maybe that was just modeling. I've only lost the stuff that I wanted to lose. But then these min-hashing, I have some approximation going on here. But once I do this, I can then quickly find the similar items. So I've been trading off modeling and some approximation for speed, right? And that's really, when you're dealing with really large data, this really turns out to be the problem. How accurate do you want to make the models versus how long are you willing to pay for them? And we've started from the modeling and gone towards making it efficient. We'll get back a little bit to modeling things on Monday, talking about some different options for distances. So this is really all about speed. Okay. All right, so I've got about 20 minutes left, so let me show how to do locality-sensitive hashing for Euclidean distance. So I need to come up with a new hash function now. This hash function was specifically for sets. Now I have these vectors, these potentially high-dimensional vectors, right? So again, I mentioned that if we have a one-dimensional space, we have one-dimensional values, then we can just sort them. If we have 2 to 12-dimensional values, somewhere in there, we can use something like a kitty tree, and I'll talk about some versions of this next week, Wednesday. But if we have really high-dimensional vectors, this becomes really hard. And we'll, all right, so this is, so the input is going to be some vector A, and I'll say this is an RD. So this is in d-dimensional Euclidean space. If you're not used to this, so that means that I can write A as A1, A2, up to AD, and each of these are going to be some real values. Okay. All right, so my hash function, I'm going to find a hash function U in 2 steps. Well, maybe in 3 steps. So first one is I'm gonna pick a random random unit vector U. So this is, you can say a unit vector is in. So this unit vector is a d-dimensional vector, but its norm, its length is 1, right? So then, second step, I'm going to create a U, which is going to be a dot U. So the dot product, if you're not familiar, is right. So I take all the coordinates and I multiply together the 2 coordinates, and I add all these things up. This is a dot product. Okay. So this is a contraction. So what this is going to look like is that I've got some high-dimensional space, high-dimensional space, and this has a point A in it. And then I have a unit vector, so I've got this unit ball, and my unit vector U is on here. And so I can think of extending this unit vector so it's a line. And then this dot product is really a projection. Right? So this is AU. I'm projecting to a point on the one-dimensional line, the one-dimensional vector that goes through U. And that's the dot product is telling me now this length. So this A dot U is now a scalar value, right? But it lies on this line, so I can think of it as a value. So this A dot U is a value now on this line. So that's what the dot product is doing. Okay? So now 3, I'm going to, so 3 I'm going to, I'm going to bin vector U into cells of size 1. Okay? So what is this going to look like? So this is going to look like where, and these are going to be randomly shifted from the origin as well. So where the distance here is gamma. Break these up into bins. Right, so now I've got this, I've gone from this d-dimensional space to this one-dimensional space through this vector u, and then I break it up into these bins. So now so a hash is defined by this unit vector u, 2 points are the same if they fall in the same bin. So now it says that A and B are the same if AU and BU in the same bin. And remember, these are now one-dimensional values, right? So I can sort them all, and I broke them up into bins. I can pick a random offset, and then I can kind of it's some value. I can say this is starting at this value is bin 0, this is bin 1, this is bin 2. So I can assign them each an integer, in fact. And if they have the same integer, that's the hash function. That is the hash function. And then so now I'm back to, I'm assigning each of A and B an integer. This looks just like the values I have from the min hash. And I can apply the same thing. So I pick just a random high-dimensional vector, unit vector. I project onto it, using a dot product, and I bin these by taking kind of a shift and then every value gamma. And this value gamma is going to correspond to the similarity I want. So if I look back at this picture I drew here, where using the min-hashing for Jacquard similarity, I got this blue line, which is this perfect linear line. It's hard to say exactly what this line looks like for this hash function. But I can say something for inside of this locality-preserving hash function family in terms of this alpha, beta, gamma, and phi here. So basically I can say that, the details are in the notes, but there's an important step that I didn't explain very carefully, and I'll see if you can figure that out. But the basic idea is that if the distance is small, if it's less, say it's less than gamma over 2, so I use gamma here, but let's say it's gamma over 2, then they'll fall in the same bin with very high probability. Right, so if this is gamma, so it will fall in the same bin with probably at least 1/2, right? So if it fell in here, distance gamma over 2 means that, it was somewhere in this circle. This circle projected down is in this range. This range, I drew it so it looks roughly gamma. Let's say it's actually smaller. The part of it which overlaps into a different bin is at most half of it. So probably at least half, they fall in the same bin if the true distance is less than gamma over 2. And you can, it's a little harder to see the other side, but you can get some other bounds on the other side. So you can get this other, if the distance is large, then the probability they're in the same bin is small. So if the distance is outside of some ball, they're only in the same bin if they're in this part of the space, right? So they could be large, but in the direction orthogonal to the unit vector, and that turns out that's a small probability if you're in at least 2 dimensions. So you can work that out as well. So you can get these bounds for this, and so then instead of it looking like these nice red boxes, you get bounds that look like this, I think instead, and you can still amplify these using a similar trick here. So you would use the same trick as you did before with the banding in order to do this efficiently, The analysis is a little bit more messy, but the same sort of trick works. Okay, so one last thing I wanted to mention is there's one step here that I have not told you how to do. One of these 3 steps that's actually a little trickier than you might think it is. So taking a dot product is easy. I wrote out how to do this. You sum up the product of these things. Binning the vector is actually pretty easy too. You pick a random offset and then you do a mod operation once you've dealt with this random offset, and you can, actually not the mod operation, you do, you divide by that and you can kind of work out what that integer would be. So this is easy. Picking a random unit vector in a high-dimensional space, I mean, it turns out it is easy, but it's not something you might think of how to do. It's not kind of, the first guess might not be right.
Sorry, what's that? U and what?
Yeah, so let me try to write this. So this is if you're, this probably doesn't make much sense to you if you haven't taken certain math classes that have used it, but this is the d-1 dimensional sphere, which means it's a sphere that lives in d-dimensional space. So a circle, so example, so in a 2-dimensional space, then this is S1. So kind of like, this is like a blackboard bold RD, it's like a bold S where you've written it twice. And so it's a 1-dimensional surface. There's only one parameter on a circle. In d dimensions, the sphere of unit directions has only d-1 parameters because you fixed the length. So even though you have d coordinates, you have that the sum of all the coordinates squared must be 1. And so that removes one degree of freedom. So you have a d-1 dimensional space. But it's a random unit vector, a random d-dimensional unit vector. So how would you construct a random d-dimensional unit vector?